In this chapter, we will talk about the structures of atoms. We start from the discovery of subatomic particles. The atomic theory is the scientific theory that matter is composed of particles called atoms. The theory traces back to the ancient Greek philosopher Democritus and others. They thought that the objects are composed of atoms, and the properties of objects depend on the kinds of atoms. This philosophy is called atomism. The word atom originates from the ancient Greek word meaning uncuttable. John Dalton established the modern atomic theory based on his experimental results. He found that chemicals do not react in arbitrary quantities, but in multiples of some basic indivisible unit parts. Today they are known as the masses of atoms. Amedeo Avogadro established the Avogadro's law. He proposed that two gases of equal volume at equal temperature and pressure contain equal numbers of molecules. For example, 2 liters of hydrogen reacts with 1 liter of oxygen to form water. So, water is H2O. Robert Brown found that pollen grains floating in water constantly jiggled for no apparent reason. This phenomenon is known as Brownian motion. Albert Einstein proved that Brownian motion was caused by the water molecules continuously knocking the grains. He also developed the hypothetical mathematic model to describe it. Einstein won one of his Nobel Prizes for this achievement. The study of electricity was also developed as a separate topic. Ancient Greek, Roman, and Arabic naturalists and physicians reported shocks from electric fish, like electric eels. The static electricity can be produced by robbing amber by fur. The word electricity originates from the ancient Greek word meaning amber. William Gilbert distinguished the lodestone effect from the static electricity. The lodestone is a naturally occurring magnet. It was the first time the magnetism and electricity were separated. In electricity, there are 2 types of charges: the positive and negative. Michael Faraday was the greatest individual in the history of electricity. He invented the electric motor. He also related the electricity with matter. The Faraday's first law of electrolysis says the mass of the elements deposited at an electrode is directly proportional to the charge. For instance, when an electrolyte with copper ion is electrolyzed, the element copper is deposited at the cathode, and the mass of deposited copper is proportional to the charge passing through the circuit, which is equal to the integration of current with respect to time. This painting shows the scene that Alessandro Volta showed his electric pile to Napoleon Bonaparte. His pile is also called a voltaic pile. It produces electricity, which ignites the chemicals. The voltaic pile is the prototype of today's batteries. Each element in a voltaic pile is composed of a zinc plate, a copper plate, and electrolyte between them. The electricity is produced by electrochemical reaction. It confirms the correlation between matter and electricity. The discovery of subatomic particles is based on experiments with discharge tube. A discharge tube is a sealed glass tube with 2 electrodes. Inside the tube is vacuum or certain types of gases. When a voltage is applied, the electrodes are charged. The positively biased electrode is the anode. The negatively biased electrode is the cathode. When the voltage is high enough, current flows through the tube from the anode to cathode. This phenomenon is called discharge. During discharge, the discharge tube glows. When fluorescent material is applied to the inner wall of the discharge tube, fluorescence could be observed. Julius Plucker discovered something came out from the cathode of the discharge tube. Eugen Goldstein named it cathode ray. Here, I show you a photo of the discharge tube. It has a shield. The shield can block the cathode ray traveling in straight line. When discharging, there is a pink glow. A green fluorescence can be seen when the cathode ray hits the fluorescent material. The shape of shade duplicates the shape of the shield. When a magnetic field is applied to the cathode ray, the position of the shade moves. It suggests that the cathode ray is charged. The sign of the charge can be determined to be negative by the deviation direction of the cathode ray. Sir Joseph John Thomson measured the specific charge of the cathode ray. In his experiment, the cathode ray was first energized by a voltage, V. The kinetic energy of one particle is equal to the work done to it. M, V and Q are the mass, velocity, and the charge of the particle, respectively. So, the speed of particle can be calculated. When the particle enters the region with electric field, it was deviated. The deviation also showed that the particle in the cathode ray is negatively charged. Thomson then added a magnetic field. By adjusting the electric field and the magnetic field, he could make the cathode ray to move in a straight line. Under this condition, the electrostatic force balanced the Lorentz force. E and B are electric field strength and magnetic flux density, respectively. By inserting the speed of the particle we calculated before, we can solve the ratio between its charge and the mass, which is its specific charge. Pay attention that specific charge is a property of particles. Therefore, finding the specific charge of the cathode ray is equivalent to the proof that cathode ray is made of charged particles. Meanwhile, George Johnston Stoney suggested that there existed a single definite quantity of electricity in atoms. He named it electron. Thomson's experiment marked the discovery of electrons. However, Thomson's experiment could not find the charge or the mass of the electron. Robert Andrews Millikan measured the charge of electron by his oil droplet experiment. Furthermore, from electron's specific charge, its mass was also determined. Millikan's experiment was done in a chamber. First, a fine mist of oil droplets was sprayed into the chamber. The motion of the droplets was monitored through a telescope eyepiece. Some droplets were charged due to friction. Then they fall into the region with an electric field. Some of the charged droplets could reach terminal velocities. When an oil droplet moves at a constant velocity, the gravitational force, Coulomb force, and air drag are in equilibrium. R and ρ are the radius and density of the oil droplet. G is the gravitational constant. Eta is the viscosity of air. In this equation, there are two unknowns, the radius and the charge. The electric field strength is adjustable, and the velocity is a function of the electric field strength, which can be measured. Therefore, by using two different electric field strengths, we can establish two equations, which will be enough to find two unknowns. A good idea is first set the electric field strength to be 0, so that we can find the radius. Then, adjust the electric field until the droplet stops moving. Since the velocity is 0, we can easily find the charge. In Millikan's experiments, all the measured charges were negative integer multiples of some charge, E. In the form of equation, Q equals minus Ne. Here, n is a positive integer, say 1, 2, 3, etc. E is called the elementary charge. Pay attention that E is a positive charge. It is the minimum absolute value of charge determined by this experiment. The charge of an electron is the opposite of elementary charge, that is, minus E. Nowadays, the elementary charge is determined to be 1.602 times 10 to the power of negative 19 Coulomb. In calculation, we usually take 1.6 times 10 to the power of negative 19 Coulomb. This constant is extremely important and used frequently in physical chemistry. So, it is better to remember it. Combining the specific charge of the electron, we can also get the mass of it. Ernest Rutherford discovered two types of radiations from uranium. He named them alpha and beta rays. Henri Becquerel determined that beta ray is the flow of electrons because the specific charge of beta ray is the same as that of cathode ray. Rutherford and Hans Geiger determined that alpha ray is the flow of helium nuclei, which have charge 2e. Paul Ulrich Villard discovered another type of radiation. It was named gamma ray by Rutherford. Rutherford and Edward Andrade determined that gamma ray is short wavelength electromagnetic wave. Here, I show you the spectrum of electromagnetic wave. The names of the ranges of the wavelength are very important. They are frequently used in general chemistry. So, you'd better remember them. You can see that the gamma ray has the shortest wavelength in this spectrum. Goldstein discovered the anode ray from hydrogen discharge tube. It is positively charged and its mass is several thousand times of that of the electron. Rutherford and Wilhelm Wien measured the specific charge of anode ray. It was determined to be flow of hydrogen ions. The hydrogen ion was also named proton. Here, I show you the Goldstein's experiment. The discharge tube was filled with hydrogen gas. When a voltage was applied to the electrodes, hydrogen was ionized. The positively charged protons were accelerated towards the cathode. Some of them passed through the holes on the cathode. When they collided with other hydrogen molecules, glow was observed. It seemed that the ray came from the anode, so it was called anode ray. However, they come from the gas. The charge of the proton is determined to be the same as the elementary charge, and its mass is also determined from its specific charge. James Chadwick discovered that, when alpha ray from polonium collides with beryllium plates, an unknown beam of particles is radiated. When it collides with paraffin, protons are generated. Paraffin is a hydrogen-rich polymer. The particles in this radiation are called neutrons. They have zero charge, and they have almost identical mass as protons. Today, we understand that the neutrons are produced in a nuclear reaction and can kick out protons in the paraffin.